Hello everyone, welcome back to my channel. In this video, I'm going to talk about a very important topic of topological spaces, the interior of a set. Let's begin. We consider a topological space X and a subset omega of X. The interior of omega is defined as the union of all open sets that are contained in omega. And this is a mathematical formulation. To better understand this concept, we are looking at a very simple example. In this example, X is the set consisting of three elements A, B, and C. Let tau be the following collection of subsets of X. We can easily verify that tau is a topology on X and therefore X with tau is a topological space. In this topological space, how can we find the interiors of omega 1, omega 2, and omega 3 over here? Let's look at the set omega 1. The set omega 1 consists of two elements, A and C. In order to find the interior of omega 1, we are going to find all open sets that are subsets of omega 1. The empty set is open and it is a subset of omega 1. This single point set is open. It is a subset of omega 1 as well. These sets are open, but they are not subsets of omega 1. Therefore, the interior of omega 1 is the union of the empty set and this single point set. So it is this single point set. Now, let's look at omega 2. Omega 2 consists of two elements, B and C. Then it is easy to see that the only open set that is contained in omega 2 is the empty set. Therefore, the interior of omega 2 is the empty set. How about omega 3? By a similar way, we find three open sets that are subsets of omega 3. They are the empty set, this single point set, and omega 3 itself. Then their union is omega 3. So the interior of omega 3 is itself. And observe that in this example, omega 3 is an open set. Next, we are looking at some important properties of the interior. Again, let X be a topological space and let omega be a subset of X. The first property says that the interior of omega is always open and the interior of omega is a subset of the set omega. How come this is true? First of all, by definition, the interior of omega is the union of a family of open sets. And as you know, in a topological space, the union of an arbitrary collection of open sets is open. Therefore, by definition, the interior of omega is the union of a family of open sets, and therefore, the interior of omega must be open. How about the second property here? Observe that each set V in the collection we are looking at is a subset of omega. Therefore, their union must be a subset of omega as well, and therefore, the interior of omega is a subset of omega. Okay. Next, if V is open and V is a subset of omega, then V is a subset of the interior of omega. If V is open and V is a subset of omega, then V is one of the sets in the collection we are looking at. And remember that the union of them contains each set in the collection. In particular, the interior of omega contains this set V. The first property and the second property tell us that the interior of omega is the largest open set that is contained in omega. There is one more property. Omega is open if and only if omega is equal to the interior of omega. And we already saw that in the previous slide. Through an example, here we can easily show that this is true in general. Now we are going to explore further properties of the interior. A belongs to the interior of a set omega in a topological space if and only if there is some open set V in X such that this is true. A belongs to V and V is a subset of omega. And this is an illustration of this property A here, and this is omega. A belongs to the interior of omega if and only if there is some open set V such that A belongs to V and V is a subset of omega. How can we prove this property? Let's look at the forward implication. If we take any A in the interior of omega, we can use this definition for the interior and see that A belongs to one of the sets V in this collection. And V is a subset of omega and V is open. So we have this property. The converse implication is not so easy to verify. Now, in this theorem, we are looking at a metric space, and omega is a subset of that metric space. Then A belongs to the interior of omega if and only if there is some radius r such that the open ball with center at A and radius r is a subset of the set omega. What it means here is the open set in the previous example can be replaced by an open ball if the topological space under consideration is a metric space. How can we prove this theorem? If we take any A in the interior of omega, by the previous theorem, we can find an open set V with this property. And remember that in the setting of a metric space, if A belongs to an open set, there must be some radius R such that the open ball with center at A and radius R is a subset of V. Therefore, this is true because that open ball is a subset of V and V is a subset of omega. How about the converse implication? Okay, we are going to use a very important property in a metric space. That is, any open ball in a metric space is an open set. So let V be this open ball, then it is an open set. It contains A and it is a subset of omega. Therefore, by the previous theorem, A must be in the interior of omega. Now we are looking at an example. Let X be the real line and let omega be this interval. Depending on the type of topology we consider on X, the interior of omega can vary. First of all, let's look at the usual topology on X. In this topological space, the interior of omega is the open interval from -1 to 6. In the second example, tau 2 is the discrete topology. Please remember that in tau 2, any set is open. So, in particular, this set is open. Therefore, the interior of omega in this situation is omega, and it is this interval. Let's look at tau 3. Tau 3 is the trivial topology or the indiscrete topology on X. Then, the only open set that is contained in omega is the empty set. Therefore, the interior of omega is the empty set. Finally, let tau 4 be this collection of subsets of R. It consists of the empty set, the whole space R, and all symmetric open intervals of this form we can verify that tau 4 is a topological space. In X with tau 4, the largest open set that is contained in omega is the open interval from -1 to 1. This is the largest symmetric open interval that is contained in this set. Therefore, the interior of omega is this open interval. Finally, I am going to have one question for you. Let X be a metric space. Is it true that the interior of any closed ball in this metric space is the corresponding open ball? Some people think that this is true. Nevertheless, this is not true in general. Let X be R and let D be the discrete matrix on X given by this formula. Then we can show that the closed ball with center at A and radius 1 is the entire space X, while the corresponding open ball is just this single point set. And please remember that in this metric space, any set is open. Therefore, the interior of this closed ball is itself, so it's X. And this open ball is just a single point set. They are not the same. So this is a counterexample for this property. To know more about the discrete metric space, please see the link in the description below. On that link, we will see the definition of an open ball, closed ball, and some properties of sets in this metric space. This concludes my video on the interior of a set in a topological space. Thank you for watching.